Concept 2 is principle of equilibrium. What does an equilibrium means? It means the output balance the input in any system, or the upward balance the downward. Now, how can we model a differential equation with an idea of equilibrium? It will be illustrated in the examples to follow. Example 1 is the variation or fall of atmospheric pressure with the increase of altitude. Let's try to formulate a differential equation which will explain this natural phenomena. For this, let us assume atmosphere as column of air with constant cross-section area A. Let us divide this column into boxes filled with air of thickness del Z. Pressure at lower face of the box will be Pz. Pressure at upper face of the box will be Pz plus del Z. Now we can calculate force downward as pressure downward times area of the box. Similarly, force upward will be the pressure upward times area of the box. Now let's try to keep equilibrium principle into action. That is, upward force on the box is equals to downward force on the box plus weight of the air in the box, which is also contributing downward. We already have information on both the forces, so let's try to figure out weight of the air in the box. We know weight of air or of any material is equals to mass of the material, that is air, times acceleration due to gravity, where mass of the material can be further expressed as density times volume, where volume can be further expressed as base area times height. In principle, density varies or decreases with altitude, that is Z, but for our purpose, we will consider our box to be very shallow, so density stays same within a box. Finally, we will arrive at this beautiful expression. Now let's try to formulate differential equation from the expression we have. To proceed ahead, you need to refresh your memory of first principle of derivative, which means the derivative of a function f with respect to x can be expressed as a small h amount of change in the function f, that is fx plus h, minus the unchanged or previous value of the function fx divided by the very small change h, but within a limit that small change h tends to 0, or in other words, h is very small in value. And for our expression above, del z is our h, so when del z tends to 0, we can write left hand side of the expression in terms of dp by dz. Now this is in particular is the differential equation explaining the rate of change of pressure with respect to altitude. But do not forget, the differential equation we write initially may not be the appropriate to solve for a variable we are interested to solve. It may contain other variables which we have to eliminate. The elimination part I will leave you to explore, as the objective of this video is to help you formulate differential equation from the scratch of any physical phenomena. Example 2 is on water flowing from a small hole of a bottle or a water tank. The height of the water inside a bottle is y, the area of a hole in a bottle is a, and water is flowing outside from the bottle at a velocity v. Now we need to find a differential equation which will determine the way the height y of the water level above the hole varies with time, in short dy by dt. In order to use principle of equilibrium, let's see what is in balance here. That is, volume of water exiting outside is in balance with volume of water stored inside the bottle. In a short interval time del t, the volume of water exiting outside is equals to velocity of water times time interval times area of the hole, that is v times del t times a. The best way to check any new expression in physics is by checking the dimension. For our case, it has a dimension of volume, so this indeed represents a volume. Similarly, volume of water decreased inside a bottle can be calculated by subtracting the initial volume to the final volume in a time interval del t. Now let's rearrange our expression. Remember the concept of first principle of derivative. At del t tends to 0, meaning at very small time interval, we can write left hand side expression as dv by dt. But look carefully, it's volume v the variable we are interested in. No, it is a variable y, the height. So replace the variable v by y. Finally, you arrive to the differential equation, which is a mathematical model for our physical phenomena expressed in the form of variables of our interest. But wait, is it the velocity you want in right hand side of the equation? No, you want height y. Here I would encourage you to take help from Torricelli theorem, which gives you a relation between velocity v and height y. Again, the point of this video is not to derive full expression, rather it is to give you a glimpse on how we can formulate differential equation by utilizing the concept of equilibrium.